Okay, let's talk about implicit differentiation. So when we say implicit, what that means is we're not able to explicitly solve for y. So an explicit function, let's just talk a minute. We'll look at that guy maybe later. An explicit function looks like f of x is just some y. Y is totally a function of x. Like, I don't know, maybe y equals 3x squared plus cosine of x. Y is on itself by one side, or by itself on one side. All the x's are on the other. If I had maybe 3x plus 2y equals e to the 5x, I could solve this for y. I could solve it explicitly for y. So I move the 3 over. At 3x, divide everybody by 2, and I have solved explicitly for y. Sometimes we have a curve in space where it's not possible, or at least not easy, to solve for y. If we say had this guy, it's mathematically impossible for you to write this curve as y equals a bunch of stuff that only has x in it. Even if, like, you think, oh, I'll just move that guy to the other side, and you'd maybe write this. Oh, see, I've still got y's over here on the right. I've got y's on both sides. It's impossible to get that y out of the sign and write y equals just a function of x. So sometimes we still want to know how quickly a curve is changing, even if we don't have an explicit function. And then in those cases, we use what's called implicit differentiation. And the key to all of this is why we're still assuming that y is some function of x. And every time we take a derivative with y, we have to use the chain rule. So every time we take a derivative of something that has a y in it, we pick up a derivative of y prime. Okay, and now we're just going to do a whole bunch of examples of this. This never makes any sense until we see it. And I'll come back and do some of those examples. Okay, let's start with this guy. So I've got this curve, 3x plus 4y equals sine of y. There's no way for me to solve this explicitly for y. I'm going to take the derivative of both sides. So here I'll write it out. 3x plus 4y, that's a y. Derivative will be sine of y. Derivative. Derivative's a linear operator I can distribute. So derivative of 3x with respect to x is just 3. The derivative of 4y, so I treat y just like it's a variable. That 4 is going to come along for the ride. But every time I have a y, this is a chain rule. The derivative of 4 times a function is 4 times the derivative of that function. What is the derivative of y? Y prime. Again, over here, chain rule. The derivative of sine of anything, no matter what is here, the derivative of sine of anything is cosine of that same thing times the derivative of what's inside. What's the derivative of y? Y prime. So I take the derivative just like normal, but every time I took a derivative of y, I pick up this factor of y prime. And then what we're going to do every single time, you're going to have some stuff that has y prime in it and some stuff that doesn't have y prime in it. So you're always going to collect the y primes, and I always go to the left. So I'm going to get all my y primes on the left. And then anybody that doesn't have a y prime, I'm going to take to the right. So I took this guy over here to the left, took this 3 to the right. Notice everybody here, I have 3 terms total. This is a term, this is a term, and this is a term. Everybody on the left, every term has a factor of y prime. Everybody on the right has no y primes. Remember, terms are the things in between the pluses and minuses. Okay. So since everybody has a y prime, every single time I'm going to factor out that common factor of y prime. So if I factor out that y prime, what's left over? I'll have a 4 minus a cosine of y. And then this stuff is just multiplying y prime. To get y prime by itself, I'm just going to divide that over. And we're done. So we're going to take the derivative like normal, but every place we see a y, we have to remember that y is a function. So we might have to power rule, we might have to chain rule, and we're going to pick up a y prime. We're going to get a whole bunch of terms. Every single time we end up with a linear equation in y prime. It's always possible to get all the y primes to one side, factor it out, and divide. Let's do another example. Okay, so my goal here is to find y prime. So I'm going to take the derivative with respect to x of everything, of both sides, of every term. So I've got 1, 2, 3, 4 terms. On this first term, that's 2 functions multiplied together. Y is not a constant. Y is a function. So I've got 2 functions multiplied together. So I'm going to have to do product rule here. Derivative of the first, that's derivative of x to the 5th, leave the second alone, plus derivative of the second. What is the derivative of y? That's y prime, times leave the first alone. So that's a product. I had to use product rule. Here, I've got to use chain rule. Y is a function. Like maybe I think students would get implicit differentiation better if we just carried around f of x everywhere instead of writing y. But then it just gets so messy. Y really is f of x. That's 3 times some function to the 7th power. So when I do power rule here, I have to do chain rule. I've got some function raised to the 7th. That guy's derivative would be 7 times, leave the inside alone, to the 6th, times the derivative of the inside. So 7 times 3 will be 21, and I wrote 31. 21 y to the 6th times the derivative of the inside. Every time you see a y, you're going to pick up a y prime. Next, cosine of y. The derivative of cosine of anything is negative sine of the same thing times the derivative of whatever's inside. It's chain rule. Derivative of y is y prime. Over on the right side, derivative of 8x with respect to x is just 8. Okay, now let's look at all of our terms. I've got 1, 2, 3, 4, 5 terms. These 3 terms have a y prime in them. These two don't. So I'm going to keep everything that has a y prime on the left side. Everybody that doesn't, I'm going to move to the right side. He's already on the right. So I get y prime, x to the 5th, plus 21, y to the 6th, y prime, minus sine of y times y prime equals 8 minus 5x to the 4th times regular old y. He's not a y prime. He's a their old y.
Okay, I found this on the web for regular old y.
I don't know what it's doing. Go away. Okay. Everybody here has a y prime in them. Factor out that y prime. Write down everything that's left. You might have some y's in here. That's okay. You might have some x's. That's an ugly. And then your last step, always, whatever's sitting here beside the y prime, divide. And then write all this out. And there's our derivative. So this will spit out slopes along a curve. So this graph here is some curve in space. It fails the vertical line test. It's not a function. If it were a function, we could do this explicitly. So what this is saying is, I can tell you the slope of tangent lines along some curve, but you don't just give me an x value anymore. If you just told me x equals 2, you might mean that spot or you might mean that spot. You got to give me now an x and a y value. So you tell me an x and a y value, so maybe you tell me that point, and I'll tell you the slope of the tangent line at that point. So y prime here will end up being a function of x and y. It's a function of two variables. Okay, let's do another one. So I've got this curve here. I want to find the equation of a tangent line at some point. I don't even know what this curve looks like, but it's some kind of hyperbolic curve, it looks like to me. Okay, so we're going to take the derivative of everything. Just distribute the derivative. The derivative here, that's a product of functions. So I'm going to have to use the product rule. I'm going to get derivative of the first times leave the second alone. Plus, now I'm just looking at y squared. The derivative of y squared, derivative of anything squared, is twice that thing times the derivative of whatever's inside. Every time you take a derivative of a y, you pick up a y prime. So look at that, make sure you get that. That's just product rule on these guys. Now, again, I got to do product rule here. I've got two functions, 5x and y. Derivative of the first, 5. Leave the second alone, plus derivative of the second. Derivative of y is y prime, times leave the first alone. Over on the other side, derivative of 14, that's a constant. His derivative is just 0. Okay, so now I'm just going to clean this up a little bit. 2x squared y plus 2y y prime plus 5y plus 5x y prime. I just wrote this guy in a slightly different order. Equals 0. Okay, we've got 4 terms. 1, 2, 3, 4, 5 terms. These two have y primes in them. These 3 don't. So everybody that doesn't have a y prime, let's get them to the other side. And then your next step every single time. See how I've got two terms and both has a y prime. I can now factor a y prime out from this left side. If you can't do that, you've done goofed. This will always be possible. And then divide over. Y prime will be negative 5y minus 2x squared y over 2y plus 5x. Let me make this smaller to give myself some space here. I'm gonna need a lot of space. I'm going a lot smaller. And then a little mark there we don't need. Okay, now I want the equation of a tangent line. I already know a point on the line. This point satisfies the equation of this curve. Like we could check it. I could plug in 2 squared times 1 squared plus 5 times 2 times 1. And I bet you we're going to get 14. That's 4 plus 10. We get 14. So that's a point on the curve. So this curve, I don't know what it looks like, but I know it passes through the point right there, 2, 1. This guy is going to tell us the slope of the tangent line right there. That's not a very good looking tangent. So the slope of my line will be y prime evaluated at. That's what this little vertical line means. Evaluated at the point 2, 1. So that will be negative 5 times 1, y is 1, minus 2 times 2 squared times 1. I'm plugging in 2 for all the x's, 1 for all the y's. Okay, so what do we get? Negative 5 minus 8 would be 4. So negative 13. You guys can check my arithmetic. Over 10, 12. Okay, so I know a point and I know the slope. Remember, when we're asked for the equation of a tangent line, point slope form is your best friend. If we want it in slope intercept form, we can always find it later. But point slope is your best friend because I know my x value, right there. I know my y value, and the derivative gives me my slope. So we get y minus 1 equals, if my arithmetic was correct, negative 13 over 12, x minus 2. There's the equation of our tangent line. Okay, let's do another one. So we've got this cool looking curve here. Does not pass the vertical line test. So I can't do this explicitly. I can't just say y equals a function of x and just take a regular derivative. But I can find an implicit function, it's right here, and do implicit differentiation to find y prime that still spits out slopes of tangent lines, but now I have to give it, instead of just an x value, I can't just tell it x equals 3/2. X equals 3/2 could be that point, or it could be that point, or it could be that point. See, I have to give you an x and a y. All right, so let's do this. So we take, it says take the derivative of everything, of all terms. The derivative of junk cubed is always 3 times junk squared times the derivative of what's inside. The derivative of y is y prime. Now, sometimes students will ask me, wait a minute, why don't you do the same thing with x? I am doing the same thing with x. The derivative of junk cubed is 3 times junk squared times the derivative of whatever's inside. What's the derivative of x with respect to x? That's just 1. So that's why we don't have to do this with x, because the derivative of x with respect to x is just 1. So we've technically been doing this all along. Okay, here, I'm going to have to do product rule. So here's my first function, negative 3x. Derivative of the first, leave the second alone. This is my second. Plus, derivative of the second, derivative of y is y prime, times, leave the first alone. Equals, the derivative of 0 is just 0. Okay, we got a couple of guys that have y primes, a couple that don't. That's always going to happen. You're going to get some stuff with y primes in it, some stuff without. Clean this up a little bit. All right, so let's see. Who's got y primes? I always like to go through and maybe underline my guys that have y primes, and then I like a little double line under anybody that doesn't. So these guys, they're going away. They don't have y primes in them. Notice I'm looking in between the pluses and the minuses. That's how you tell terms. These are all multiplied. So what do I get? 3y squared y prime. And I'm going to rewrite this minus 3xy prime equals 3y minus 3x squared. So I move those guys over. Every single time, everybody on your left-hand side should have a common factor of y prime. If it doesn't, you've done goofed. So factor out that common factor and then divide. And you're always going to get some nasty looking fraction like this. And it's going to have x's and y's in it. Y prime is going to be a function of both x and y. Okay, now I know a point on this orange line. Let's find what the slope of that line is by just plugging in here. So y prime evaluated at the point 3/2, 3/2 will be, this is going to be a nasty 3 times y minus 3 times x squared. Maybe I won't actually finish this problem. Times 3 times y squared minus 3 times x. X and y both happen to be the same thing on that point. And you guys could simplify that. Actually, I think that's just -1. Yeah, that's funny. I can look at the orange line and see it is. That's -1. It's the same stuff, just in opposite order with the opposite signs, top and bottom. Okay, so y minus y naught equals m x minus x naught, where x naught y naught is the point, that point right there. We get y minus 3/2 equals -1, x minus 3/2. And maybe it cleans up, maybe it doesn't, don't really care. Okay, I like this question a lot. So we're playing a video game. We're going in an ellipse. So you guys have taken pre-calculus. You may remember that this is the equation of an ellipse. We don't actually have to know any of this, but just so that I can draw it out, I'm going to go through this math here. I'm going to divide everybody by 100. None of this is necessary to answer the question. And I'm going to write this guy as x squared over 5 squared plus y squared over 4 squared. No, I want 2 squared, don't I? Yeah, because that would be over 4. 2 squared equals 1. Okay. That is an ellipse. with the center at the origin, and I go 5 on the x-axis, 2 on the y-axis. Not a very good drawing, but you see the point. Okay, that's this guy here. A rocket is fired when we're at the point 3 8/5. So at this point right here, I'm firing a rocket down this way. That rocket is going to come and eventually hit the x-axis right there. That's the point we're looking for. That's the point of this question. So the asteroid is coming in this way along the x-axis, and I'm going to fire my rocket right there. I want to know basically how much leeway do I need to give this thing that's coming in? Because as it's coming, I'm coming along this curve, and I'm going to fire tangentially down here. Okay, that's the setup of the problem. Okay, you didn't have to see the picture to understand that, but I think it helps. All right, we need to find the equation of this line. That's really what we're doing. We're finding the equation of this line. So we're going to need the slope of that line. So we need to use implicit differentiation. Now, I could mathematically, I actually could go, well, you know, the top half of this ellipse is a function. I could move the 4x squared over. Divide both sides by 25. So like, what would that be? That would be 4 minus 4 over 25x squared. Take square root of both sides. I'm technically supposed to put a plus or minus here, but I don't care about this bottom half. I'm up here on the top half, so I could ignore that minus there and just take the plus and say, well, that curve right there is this. I have solved explicitly for my function, and then I could just take the derivative. And that would be fine. That would work just fine. But honestly, I think it's like that was a little bit of algebra there. I would have already been done if I'd have skipped that. Let's take the derivative implicitly. The derivative of 4x squared. So I'm taking the derivative everywhere of this equation, both sides, all terms. Derivative of 4x squared is 8x. Derivative of 25y squared will be 50y times y prime. Every time you take a derivative involving y, you pick up a y prime. Derivative of 100 is 0. I could easily solve this for y prime. Move the 8x over. And then divide. Y prime will be negative 8x over 50y. Okay, now, kind of running out of room here, so I'm going to make this a little smaller. And I'm going to clean up this stuff from the last slide. Okay, now I know a point on that line. I know this. I can find the slope. So y prime evaluated at the point 3 8/5. Now the fact that I've got an 8/5 there and I've got an 8 over 50 here makes me think I might want to clean this up, or I might not. Let's just plug and chug and see what happens. So negative 8 times x over 50 times y. Oh yeah, this looks like this will clean up nicely. So down here, I'll get 10 times 8, I'll get 80. So I'll write out that step. Negative 8 times 3 over 80. get a little canceling there. I think I get -3/10. So the equation of this line here is y minus y naught equals the slope times x minus x naught. I want to know, where does that thing intersect the y-axis? So let's draw just that part out. I'm at this point. Was it 3 3/8? Yeah, 3 8/5. This is my line coming through here. I want to know this point on the line. Well, right there, my y value was 0. That's really what I'm finding. Where does y equal 0? So I'm just going to plug in y equals 0 and solve for x. So 0 minus 8/5 equals, again, distribute there, -3/10 x plus 9/10. So now I just got to do a little cleanup. So let's move the 9/10 over. So just a little adding fractions here. Minus 9/10 is -3/10 x. So this will be what? -16/10 minus 9/10, which is -25/10. And that's supposed to be -3/10 x. The 10s cancel. I think we get x equals, you guys definitely check my arithmetic here. I think we get x is 25/3. So that'll be the x coordinate where this rocket intersects the x-axis. So that was an interesting question. I think there was one more. Okay. So here we have the equation of a circle, and they asked us to find the second derivative of y. So we're going to take this just a little further. This equation right here, by the way, is just a circle of radius 5. So if I take the first derivative with respect to x of both sides, I'm allowed to do that. Then derivative of x squared is 2x. Derivative of y squared is 2y times y prime. Every time you got a y, you pick up a y prime. The derivative of 25 is 0. And now I could, if I wanted to, it does clean things up, just divide everybody by 2 here. 0 divided by 2 is 0. I get x plus y times y prime equals 0. Now, they asked me for the second derivative, so I'm going to use this version here to find the second derivative. But just for fun, let's work with this guy a minute. X plus y, y prime equals 0. Move the x over. Divide by y, y prime is -x/y. So that formula right there tells you slopes of tangent lines to a circle. So the point, let's say 3, 4 is on that circle. Point right there, 3, 4. I could find the slope of that tangent line, which would come through like this. The slope of that tangent line I just drew, I just plug in a 3 for the x, a 4 for the y, -3/4. What about the slope right here? That's at the point 0, 5. So evaluated at the point 0, 5, Look at the picture. Look at that. That's a horizontal slope. Oh, I get -0/5. I just get 0. Okay, so the circle is going to come up a lot. We're going to do a lot of implicit differentiation kind of problems with this. All right, now let's finish answering the question. They wanted second derivative of y. So I want y double prime. So I would go through again and take another derivative. So we take the derivative with respect to x of everything here. Derivative of x is just 1. Here I've got a product of functions, y and y prime, both depend on x. So this is a product of functions. I have to use product rule. Derivative of y is y prime times leave the second one alone. Derivative of the first times leave the second alone, plus derivative of the second. The derivative of y prime is y double prime times leave the first alone equals 0. So this says 1 plus y prime squared, not second derivative, y prime squared plus y second derivative times regular y equals 0. And then I could, if I wanted to, solve this for y double prime. So y double prime will be, let's see, what do we get? -1 minus y prime squared all over y. But I know y prime, it's right here in terms of x and y. So y double prime would be -1 minus a negative x over y squared all over y. And this could be cleaned up. Oh, I wrote a 2, sorry. This could be cleaned up a little. Like when you square a negative, it's going to be positive, and then I can get a common factor of y, and then this y is going to cancel. Like some stuff would clean up a little. So maybe let's do that. Because I think this is going to get a little prettier. So this would equal -1 minus x squared over y squared. That minus came, that one got canceled, all over y. Now I can get a common denominator of y squared here. So this would be -y squared over y squared minus x squared over y squared all over y, which would be -y squared minus x squared over y squared all over y. And then I could do a little keep change flip. That would be -y squared minus x squared over y squared times 1 over y, which is something nasty looking like this. So that is y double prime. Is that much prettier? I don't know. Maybe it wasn't helpful to go through this. I mean, I think it's a little cleaner. I was hoping the y's would cancel out, but they're not going to. Okay, let me see if I want to do any more of these. I think that's a good start on implicit differentiation. So now I highly recommend you go in, try some of these extra problems. I made a whole worksheet on implicit differentiation. And then there's a whole video if you want more examples. Okay, that's a good place to stop there.